Yeah, yeah. Sorry. There was some. Okay. No, no, it's all right. I heard about it in mid of the way, but I can start my. I can start. Okay. So is it audible and is it visible to everyone? Okay. So should I start or should I start now? Oh, okay, fine. Okay. So very good morning to all of you, and I am Professor M. Sharma, Professor and Head in the Department of Electronics and Communication Engineering, and I am going to start. I am going to deliver the expert lecture in the conference, IEEE SILCON subsection conference, which is going to be organized by National Institute of Technology, Agartala. Uh, Let me do one thing. I'll switch off the camera. I hope I am audible and the things are visible. So the title of the topic is I'll be talking about the evolution of antenna and the recent developments for 5G and beyond. I have planned it for starting from the beginning where we started, the communication through the mobile started and where we are. So this is a basic, I'll taken the help of my researcher and some internet and other material also. So it contains is talking about the history, then types of the different type of the communication system which are going to be used. Then I'll be talking about the introduction of the antenna, the fundamentals of the antenna and different types of the antenna which are going to be used for the communication technology, specifically for the your mobile communication. And then there, what are the antennas, different kind of the antennas which are designed for the 5G applications and for the research. If we talk about the history of the communications, then we remember that the communication existed earlier also. The mobile was not there, but there was a communication with the different type. Like in the early days, the literature reveals that the communication established through the signs and the signals, which were used to transfer the messages. And I remember I studied that earlier also, and probably in the villages or in the tribal areas, still the drums are going to be used to give the some messages. We use the pigeons are also used some form of the medium to communicate the messages from one point to the another point, or the eagles are used. Still, they are going to be used. So the communication was used either by the then I have visited sometimes go at the Bhopal nearby. There was some Bhimtal, some lake, some caves are there where the signs are used to have some messages to communicate the messages there. So we can say that earlier the verbal communication, along with the verbal communication, but there are the different techniques like cave paintings, letter writing, drums, and others were used for the communication. As the technology grows, the man grows, the human, the society grows, the style of the communication, there are the developments in the communication in the technology. So depending upon the communication channel, we can divide it in the two categories. One is a wired and another is a wireless. We know about the wired. the parallel wire communication, or that we are going to use in the, like in the telephone lines. You have seen that there are the telephone lines which are along the railway lines. Might not be exist right now, but earlier there was some telephone lines were there along with the railway line. So there was some parallel wire communication, or the some twisted wire communication, coaxial wire communication. Still we use the coaxial wire communication for the like from communicating the signal for the high frequencies, or the from high power, not for high power, but when we have to connect with the your base station to the your some set. So we use a coaxial cable, or the waveguide we use it. And the latest which we are going to, we know about the optical fiber that's going to be used for the high speed communication. When we come to the other side, there is a wireless communication is there, and that's going to be used upon depending upon the type of the application. Either it's a ground wave, or it's a space wave, or it's a satellite communication that's going to be used. We know about with the communication systems. We know whenever the communication has to be take place through the antenna, the wireless communication is going to play a major role. And this technology is going to be used in various applications, like in the, it's going to be used in the multi sectors, it's going to be used in the cellular communication, or in the smart homes, or it's going to be used in the computers also. When we have to use the wireless communication, then without the antenna it's not possible. The antenna is the major thing, is the thing which is going to provide from your transmitter to the space. This is the interface, and then there is a communication channel. Different, it may be the space, or it may be the air, or whatever the kind. So the EM wave travels, and then it reaches to the receiving antenna, and then it is decoded or processed, and then the useful information is delivered. So the extensive efforts are going to be used to develop the multi-radio on a single module to address many wireless communication services over a wide frequency range. And the live example we can say that is going to be used for the 5G. When we talk about the communication systems, these are the following examples, like internet is there, that's going to be used. PSTN networks are there, intranet is there. Television, definitely it's a one-way communication, then there is the application which is going to be used the communication. It's a mobile set is going to be used for the communication. This we start with the basic of the definition of the antenna that you have seen in that. I have taken from the different side, but I use the Bellani's book, Antenna Theory, and it starts. Usually I ask what is the radiation mechanism, and that's interesting that if you find that the transmitter is there, then there is a transmission line, and there is a dipole antenna, and here the wave is your departed from here in the first quarter, second quarter, third quarter, fourth quarter, and then is the travels the wave is detached from this one from the antenna, travels through the communication medium, and reaches to the receiving antenna, and then there are the transmission lines and the receiver. So basically that I am just started from here where I start usually with the fundamentals of the antenna. Then what is the need of the antenna? The first statement is that whenever we have to make the wireless communication, antenna is needed. Now we may have different points. There may be the different kind of the communication systems. The slide shows that there is a one-way communication that's going to show. So there are the houses are there, and some DTH antennas, or the some parabolic reflectors are there. Dish antennas are put up. So how is going to be communicated? So we have to communicate. There is a one, either is going to be with some, like we can say the transmitter at the placed at the very high, or it may be a satellite communication. From the satellite the transponder is there, and different service providers like your Airtel or the Tata Sky, so they are going to provide their services. So they are going to have different transponders which are spaced at some low level orbit, some low orbit, and then is going to provide the communication. Then we have different type of the antennas, and I have just prepared the slide here which gives a wire antenna going to be used a dipole, monopole antenna, helix antenna, and these are the applications that is going to be used. And earlier, the wire antenna was used for the early mobiles also. Aperture antennas, we know that it's a waveguide that we see in the laboratory also, and for the high power we use the aperture antennas, reflector antennas that are going to be used for the satellite tracking and the radio astronomy. You have seen that in the pictures for the communication with the like moons and or for the different far stars. We are going to use big uh, reflector antennas going to be used. Then these are less antennas and latest which we started in 1980s that microstep antenna, and there are the different variations that we use as a ultra wideband or the so wideband, broadband, different kind of the microstep patch antenna that's going to be used with either it's either for the gain enhancement of the gain or the enhancement of the bandwidth, or it may be used as a for reflecting surfaces or absorbing the waves. So different kind of the applications that with the different designs that we are going to use for the microstep antennas. Then we started with the 1G, 2G, 3G, 4G, and latest where we using with the 5G started in the 2020. I remember that 4G came around for 2011 and it started in the very few cities. And I remember when I visited the Pune, it was around 2011 or 12 where it started. So all the generations they are going to provide the voice. Only the technology is going to change how it's going to provide the voice communication. The important thing is that if you see that the data rate is going to change and the different kind of the applications which are going to be supported or provided by the different generations varies. If you look here, the first G is going to be provided with the started in the 1981 is only the only voice. And you look the shape of the design of the antenna is going to have a external antenna, the wire antenna or the Alex antenna that's going to be used here in this one, in the first generation. Then later on, after 10 years, almost 10 years, the 2G came and it started with the text messaging also. So there's a communication, voice, and there is a some data in form of the text messages that's going to be transferred. Then I remember around 2.5G came in the 1997 where I was living at UK. Then the mobile was there and I remember the cost of the call was around, and the, say in India also around 1998 the mobile services started, and the cost of the incoming call, I remember it was a 32 rupees per minute. You can imagine where it is free now, unlimited call, whereas in around 2000 era, whenever you receive the call, you have to pay. So when you are going to call, you need to pay. Of course, we are going to pay today also, but when you are going to receive the call, that was the era in 2000. You are going to receive the call, you have to pay for listening the messages to talk. So there was a 2.5G, then there was in 2001 the 3G came, where it started along with the two applications like voice and the SMS. It started with the internet also. And I remember that the handset, there was a different kind of the handset. It was a Nokia. The Nokia handset was there. I remember it was a 2003 or 4. It was a 6600 Nokia, which has the first camera phone which uh, which was introduced by the Nokia in the market. It was having the 3G supporting to Symbian operating system and having some camera. That was of course the quality of the picture was in the VGA. Then later on, and still we use like 4G. Still the 4G is available at our country at some distinct stations where we have like three applications like voice is there, text is there, internet is there, and then it started the video calling also. Although in the 3G also the internet there was a video calling, but it was not successful. But at the era of the 4G, the video calling started, and then the 5G, all the four existed, and then again with the smart handsets, we have smart handsets. So the devices also came. The technology also introduced in the devices. So you can have with the car, or you can have some cars or something. And 6G is predicted, where it will be have the some different device to device contact can be there. And the 5G, they probably is going to use like the driverless cars are they going to be used. Some communication is going to be used. Okay. Then the mobile antenna evolution where it starts. Just I'll take a few seconds, few minutes only. You started how the mobile antenna. It's a long antenna that I have shown in the first figure. You look here. It's a long antenna, wired antenna. So mobile monopole or the whip antenna is going to be used. Take too much volume. It was really bulky. It was very heavy also. It was not. We are not easy to put in the pocket. And it was designed for multi-band for the high SAR. Definitely, a specific observation rate was very high. It was then there was a came later on with the smaller size and reasonable efficiency. Then the helix antenna came, and then the monopole again. Then we had something. The external antenna was there, and then later on I remember it was with the when we have like Nokia phones. Yeah, I remember 1100 or something. The smaller phones, and it started to use like uh, inverted F-type antennas. So if it was placed inside the your casing, which has a low SCR also, and it is going to provide your facilities here like communication and the text messages have some lower efficiency and lower bandwidth. Then we have some I find that we say the inverted F-type antennas with uh, some improved version of the PIFA, and then we have like printed monopoles later on, and the latest that we have seen in the metal chassis also, like in the iPhone, is going to be used as a chassis as an antenna. So there are some engravings are there in the backside of the that chassis, and then it's going to use an antenna. You see the different kind of the phones that are going to be used. Earlier it was a very high bulky mobile going to use as the external antenna. Then the external antenna disappeared. Then it was only the text, the smaller window, and later on with the Symbian, and then later on some advancements of the mobile operating system. We have different antenna generations and different mobile generations. Now we have the smart mobiles where we can have with the touch screens are there. Just if we slide it, some there are just some advantages and disadvantages of the first G where we started with the. You see the frequencies around 150 megahertz and the 900 megahertz and the analog telecommunication having the very less bandwidth of 30 kilohertz and say very bad voice quality, drop rate, poor battery, and very high SAR. Then we started probably the mobile in India. It started with the 2G or the 2.5G. I remember it. It started early 2000, so it was 1997 or 1998 where in India it started. And the frequency that going to started with the 1.8 gigahertz or the 900 megahertz as for the GSM mobile. And you see the bandwidth change from the 19900 megahertz, and where earlier it was only the 150 megahertz, it started to have 900 megahertz for the 2G. Then it was some digital or GSM capacity data rate. The data rate was a 64 Mbps. However, before switching to the 3G, the 2.5G came, where it was introduced as a GPRS was global positioning was also introduced. GPRS was introduced. Some email was introduced. Web browsing was introduced. Although the speed was very low, and the camera phone started. As I told, that is a Nokia 6600 where it started. Then the 3G came, proper 3G came, which has a different higher bandwidth, 1.5 to 15 megahertz, and the frequency was again the same, almost in the same range, but 2 gigahertz. But in the 3G, you see the CDMA, the technology that's going to use CDMA and the UMTS, and the age was introduced apart from the GPRS. The age was introduced in the 3G, and the capacity also increased from 144 kbps to 2 mbps. And it was better then because it was having some video calling also there, some bandwidth was there, some mobile TV came, Then in comparison, there is a 1G or 2G, it was the fast communication was there. And we called as a smartphones. Then the 4G that we are going to use, still we are going to use the 4G, having the different frequency ranges. Bandwidth is around 100 megahertz, but you see that it's going to use a long-term evolution, LTE and the Wi-Fi protocol that's going to be used. Capacity is very big. It's 100 Mbps if you compare with the other one. 3G and 4G, no comparison, but 4G to 5G, again, there will be no comparison for the capacity. And if you look here, why it's we call it's a magic that's going to provide the services like mobile multimedia, anytime, global mobile support, integrated wireless solution, and customized personal services that we can use. And you see the quality of call is going to be introduced. Is a very good QoS and the high security and the high battery usage that's going to use. And these are the different applications that we say that localized, organized services are there. And entertainment services that people are going to use for this games. It's going to use for some home also, then mobile e-commerce that you can use for the 4G applications. But real that we came with the like smart antennas, the MIMO also introduced, IPv6 was introduced, and technology the where we are using as in the 3G, the CDMA technology or the UMTS was going to use, it was replaced by the OFDM, and then software defined radio was also introduced in the 4G. Then these are the advantages that we have already discussed. The higher bandwidth is there. The response time is 10 times faster than the 3G, working at higher frequencies, 2.6 gigahertz. Better streaming. You also experience that is a streaming and the buffering is very high, high capacity and the high speed. So they are definitely there are the disadvantages. When you have the different applications, multiple equations, then the battery usage will be more. And we have the like you see, we have a now it's a habit. We are going to switch on and switch off, and probably it's a more than probably it's 100 times that we switch on and switch off. I was just reading a newspaper where a person is going to use switch on switch off more than 100 or 500 times, depending upon person to person or his free time. So the addiction has become and it's a complicated hardware definitely when we have a different kind of applications. It's a different upgraded version or the complicated hardware. The power capacity, the chip power consumption is going to be used. So why 4G? So we needed there is a need, so we went for the 4G, and still there is a need, so we went for the 5G. But this is a comparison that we already discussed. Why the 3G over the 4G? It started 201, 2010. We CDMA, now it's your OFDM is going to use. And the core network is PSTN, it's completely IP based. So you'll observe that is a 4G or 5G. Sometimes you will see that the GSM calls, they are going to use also the IP address. Like it's going to use through the Wi-Fi also. Data rates is very high. It's going up to the 1 Gbps for the 4G. It's better for the virtual navigation for the security and other applications. Now we come in the era where we are in the present, where we are having like 5G, high speed and the capacity. Definitely, it's a high speed. You see that you can download the movies and quick few minutes only from the internet. So faster data transmission is there in the 5G and then the 4G. Then the interactive multimedia. Okay, you can have like you can browse like Prime Video or the like another any other application that we can have, and you can watch the movies having very good data rate, download data rates. The voice streaming is better, video streaming is better, and they are much more efficient. And you look here in the configuration here, like in the 5G handset, this is the chassis where we have a different kind of the antennas for the sub-array A, sub-array B, C, D. This is sub-array A, B. So they are all going to be used for the different applications in the one handset. And you see that the data rates from 3G, from kbps comes to the mbps, and the 5G is going to gbps. So kbps, mbps, and gbps. Then this is a 5G technology vision, where the objective is that the data rate has to be from 1 Gbps to the 10 Gbps, low latency, less than 1 millisecond can be achieved in the 5G using the millimeter wave. Probably that's going to be used. Traffic load is decreased. This is the biggest advantages, and higher bandwidth can be used for the carrier aggregation. Then the one of the important thing that's going to be used here is going to be used as a dynamic beam forming. Is going to be employed for overcome path loss at high frequency. That's very important figure. That's going to be used in the 5G. Then these are the different kind of the applications that's going to be used for the 5G application scenario. If we look here, is a I have just placed here like enhanced mobile broadband, ultra URLLC, that is the ultra reliable and low latency communication. Then we have a massive machine type communication, MMTC. And you look at the different subset of the applications like 3D video USD screens are there, work and play in the cloud. Then we have a augmented reality that's going to be supported into the 5G. Industry automation is there, and then we have a smart city that's going to be used in the 5G. That is the application of the massive machine type communication. There's a subset of this one. And then the home and buildings are going to be used as a smart handset. So if you buy with I see that if you want, you can switch on your lights or switch off your lights, fans, like say, hey Google, switch on the light or switch off the light. Similarly, there are the devices, the applications where with the voice command you can switch on and the switch off the whole applications in the home. So the smart homes that are going to be used. So yeah, eMBB multi gigabit per second, ULCC including very low latency time, and MMTC including there are the different massive machines like IoT connections are there that's going to be used for the smart city. Then these are the 5G uses for the socio-economic responsive perspective. If you look here, the house I gave that the home security applications that is going to be used for the consumer electronics, for the remote control, uh, we can use it for the safety and the lifeline. You can have different applications for the security, and definitely in the education you see that the the government has also introduced the virtual university, and the lectures are there, uh, where you can learn, distance learning can be done. And healthcare, I remember it that it is tremendously introduced. If the patient is there in the remote villages where the doctor cannot visit, then you have a good quality of the communication. You can send the ECG or send the EEG live. You can place some sensors on the body, and then the continuous data transmission is there, and the doctor is receiving, and doctor can immediately tell about the patient. And I remember that the many lives have been saved through this application of the healthcare using the 5G. Then we are using in the transportation also, and in the airplanes also. So there are the different types of that's going to change a scenario with the development of the 5G. Then the massive IoT use cases enabled by the 5G technologies, you look here, again, the same thing, the utility is going to change, smart cities. So your city is going to change when we call it a smart city, there are a lot of things going to change. So this is the massive IoT. The application, the agriculture is there. I have seen that the people, the students, are a lot of working, they are developing the sensors and other things. So agriculture is going to be using the 5G. They are placing the electrodes in the ground, in the like in the agriculture for the agriculture production. Then the your farmer is able to see what is the moisture, what is the other fertile land is there or not, and conclusively with the application it can say that what the seed it should be used. Either it may be like a wheat, or it may be some different kind of the we weeds can be used, seeds can be bow there in the soil. So you can know about the quality of the soil and its applications for the different kinds of the seeds. Environment definitely with the I'll say that different with the different environment. Environment is going to be is a health hazard is also there with the 5G. So you see that Electromagnetic waves are everywhere. There's electromagnetic waves. So, and the most important, that's consumer electronics is also going to be used. Wearable, some applications, some researchers are working for the wearable antennas, and the smart buildings and the smart cities are always there. These are the key enabling wireless technologies, which is massive MIMO, novel multiple access, then there is the fuel duplex, then we say the flexible duplex and advanced coding modulation. And the solutions which we are having, ultra dense networking, low latency is there, machine to machine is going to use devices. This is a device to device communication, machine to machine communication, high frequency communication, and the spectrum sharing is there. Then is the 5G antenna technology. You are looking at, they are going to use as a three bands, as the low bands, then the mid bands and the high bands. That's the below the 1 gigahertz, from 1 to 6 gigahertz, and then high bands that are going to use the millimeter waves, maybe around 60 gigahertz, or it may be that around 30 gigahertz. The figure shows that these are the existing ITU bands, and then ITU WRC and some FCC bands are there. These are the different applications in India operators. These have given the Jio, what Airtel and the Vodafone. They have like different licenses, yes, no, for the every DCLR or IMT. These are the different capacity layers that are going to use. These are the different specifications. Then these are the antenna requirements, how we are going to place the antenna in the 5G mobile, like for LTE, for the, you look here, so for LTE millimeter wave, for LTE1, for LTE2, for Wi-Fi. So these are the for the Wi-Fi one. So these are the things that we are going to use. So main antenna or the auxiliary antenna, and then 5G LTE or the Bluetooth or NFC. So these are the different applications that so we are going to place. We observe that now there are the multiple antennas. Although the I don't, it's needed that the one antenna can have multiple bands, but still there are the many antennas that are going to be used in the 5G. So it's a challenge is there to design an antenna to keep the size of the antenna the small. And the most important thing when you are going to use the multiple antenna on the same device, the isolation is there. Although 30 dB is required, but it's still at least the 15 decibel oscillation is required between the antennas, along with the electromagnetic interference has to be invited. Then the design, robust design is needed. Okay. And then antenna should meet the carrier's OTA requirements and other specifications. Then, as I mentioned, that the MIMO technology is going to be used for the 5G. And what is the MIMO technology? Just for that is going to depend upon the diversity, how it's going to be used. So it's a multiple input, multiple output that we are going to use. So there are the X1 is going to connect with the Y1, or X1 is going to connect with the Y2, or it's a YM. So there may be the some n number of the transmitters, m number of the receivers. They are going to connect to each other in the different ways. That's going to be used for the MIMO. So when we say that MXN MIMO wireless system, here we say the N symbol that can be transmitted to N transmit antenna at a time, so X1 to XN, and M symbols like up to the M receivers. Okay. Then this is a single input, single output, single input, multiple output. You look here is a single input going to communicate with the single output. Single input, multiple outputs. One transmitter, but multiple receiver. Now multiple transmitters, single receiver. So multiple transmitters, MISO, and there is a MIMO, multiple transmitters and multiple receivers. And this is now is going to, how it's going to be implemented, it depends upon the diversity techniques or the diversity gain, which is going to improve the reliability. We are looking about that the diversity. Just I am giving a one example. So it's going to the transmitter is there, receiver is there, is a one channel. So depending upon the channel, say we are saying the diversity is 0. And we go to the next one. So here you are saying that there is a fading channel. There are the two fading channels, which are transmitter is one, is going to receive two antennas with the receiver. So we are just going to replicate here. The data rate is there. So there are the two fading channels. 1011 is going to provided here. So we can say that it's a 1 into 2 SIM. single uh, transmitter, single input, and two outputs here. So diversity is 2. This is the case of the SMIO. Then we have a MIMO. So they are the two inputs and the two outputs in two transmitters, antennas. So how is going to communicate? There is a transmitter 1, there is a transmitter 2. It is going to communicate with the different feeding channels, and then we are receiving with the output with the different receivers. So this is the 5G technology. There is a massive MIMO. That's the latest topic. So which we are going to use for the smart beam or so movable beam or the beam forming that's going to use for the massive MIMO. So elevation of the beam forming is there, so we can have like, so satellite is there. From the satellite we can have, from the beam can be formed on the earth in the different patches. It may be patch at the north, or it may be the middle of the India, or it may be the south of the India. So like it's be a different beam forming, or a beam forming is there. So different, you see that different beam kind of the beam forming every MIMO beer. So it's going to put in this way, or it's going to put in the azimuthal also. So there is elevation and there is a azimuthal also. So that is a massive MIMO is going to use large antenna array that's going to be used at each base station. A line, a large number of the users are served simultaneously, and access of the base station is there. So this is a full dimensional MIMO that's going to be used. Either is going for the elevation or it's going to use for the azimuthal. So this I am going to put as an antenna array that's going to be used for vertical, or it's a for horizontal. It's going to be used. And then it is going to be used for multi-user MIMO, that we are saying that the from access point different stream 1, stream 2, stream 3, stream 4, or we can use multi-user MIMO to improve the wireless throughput by enabling the simultaneous transmission to more than 2 users. And this is all about the future. That is about the 6G and 5G. So we need to integrate the 5G with the satellite network, so we can have like BTS. It may happen that the BTS may be over, or we can have a handset when the Starlink has, if the Starlink comes, probably it will be given the permission, or the always the satellite communication will be there, so you will be able to access through the satellite, not through the BTS tower. Maybe after 5 years, or maybe after the 10 years, like, or that maybe in the 6G or in the 7G, space roaming in the world completely becomes wireless. All the homes are smart homes, driverless cars, driverless trains, all the things will be having the advanced. This is the future 6G will provide an ICT infrastructure that enables end users perceive themselves as surrounded by huge artificial brain. So, of course, the machine cannot be intelligent more than the human, because human made it. Still, we say artificial intelligence will be there. And this is why we need the generation for technological breakthrough, new services, applications, cases, always is desirable. So we'll be landing after a few years in the 6G, then the 7G, and probably 8G. And this is through the new services, new applications, new cases, probably that uh, we need not to go to the doctor. We can have all the data we can transmit online to the doctor, and doctor can see at home, can talk about it. Either it's a brain imaging, or it's a ECG or the EEG. It will go through the internet, communication satellite. All the things will change, definitely it will change. Two examples of 5G, the 5 sense interactive hologram technology, and then interactive haptic communications, where we can have like, you've seen that some holograms that can be introduced. This is some timeline. So 6G roadmap that is going to the 2031, how it's going to be produced. Not talk about much more about this. This is the 6G requirements, that the perception has to be there for infinite capacity, the most important thing. Then the 3D intelligence coverage, some protection of the, it will encapsule the AI also. Zero latency network will be there. Of course, there is a minimum latency is there, still the zero latency network, and it should use the extreme low power and the energy free connectivity. Looking to this one. So if you look to the comparison about the 5G and 6G, it will have from Mbps, it will go to the Gbps, and data rate will be tera in the tera. We talking about the giga, but it will go to the tera. Then uniform user experience. It may be the 50 Mbps 2D everywhere. It may be the 3. You see the difference, 10 Gbps 3D everywhere. So we need to think how we can achieve them. Will it be enough, or still we'll be going ahead? Okay. And you see that energy, it's in nano, it will be going to the pico. This is all comparison that how we'll be landing from 1980. We started with the where we are in the 2024. We are having LTE or the VLTE, and then 5G will be using the new techno communication will come. These are the references, and just thank to my researcher, Dr. Bhavna Kalra, who has contributed in the preparation of the slides and preparation of this lecture, all with the references. Thank you very much. Thank you. Thank you, Professor. Any query? Oh, okay, okay, okay. Yeah, good morning. Good morning. Okay, I switch off. Okay, just okay. Thank you. So, my all the best wishes, and I congratulate to organizers for this beautiful conference. Okay, sir. Okay, sir. Yeah, please, please.
Definitely, if you look to the 5G, the security features are more, the algorithms are there, and the data is to be encrypted. You see that you appreciate that whenever there was a crisis like in the WhatsApp also, some data was encrypted. There was a thing that data is going to leak, then WhatsApp came further and made the announcement that the data is encrypted.
There is a signal is also there where it's much more secure. So when you are going to have the applications and you are having the advanced technology like 5G or the 5G or higher, And when we are having, so there is you can say it's a multiple layers technology security is there, and definitely the algorithms are rigid. So probably it's unbreakable, and then the data is secured, and the information which is going to be transferred is secure. Only the encryption which we can support, so it cannot be decrypted. Okay. Okay. Thank you very much. Thank you. Thank you. So should I leave? Should I stop? Okay. Thank you. Thank you. Thank you. Thank you. I congratulate. Thank you very much. Thank you.
Okay, sure. Okay. Uh, Good morning, sir. So, yeah, I'm good. How are you? Okay. So, yeah. Mm, yeah. All right. Mm, mm,
Young professional chair of this IEEE SILCON 2024, Dr. Shailendra Singh, will be introducing our first young professional lecture uh, delegates. I welcome Shailendra Singh to come here to give a brief introduction about it.
Very good.
Hi, Khalid. I need 1 minute to start with because I think I have facing some problem to study my screen here. I would like to rejoin again.
Okay, okay. We will rejoin.
सर एडमिट करो
Exit कर.
Can I do that?
So you want to rejoin again?
You are not audible to me. I think, yeah. I would like to rejoin.
Okay.
I'm finding some problem to study my screen.
Okay, you.
Okay, thank you.
सर
Rejoin.
सर ज्वाइन करवा दो वहाँ से हाँ अभी ज्वाइन हो गए सर सब ऑडियो एंड वीडियो बोथ अराउंड
Display.
हाँ शेयर हो रहा है आपका भी हो रहा है उनका भी हो रहा है
Manen, if you come, you share your PPT later. First, just I want to share your face first, so everyone can. Then we can share after your introduction. You can share your.
अभी आ जाएंगे Sir, could you please switch on your camera, sir?
So, good morning all of you. So in respect of IEEE SILCON 2024 conference, so this we are going to start our this IEEE Young Professional Events. So today is first IEEE Young Professional Events lecture series. So in this respect we have Dr. Munendra Singh. He was postdoctoral research fellow few days back in John Hopkinson University, USA. Now recently he joined NIT Jamshedpur as an assistant professor in electronics and communication engineering department. I am glad to say that we are fortunate enough that he is, despite of his busy schedule, he become ready to deliver the session on this conference, as he has committed to deliver the session when he was in John Hopkinson at least I think 7-8 months back. So you can understand the superiority work of John Hopkinson in medical imaging. So I think it is world's second highest ranking university that deals medical imaging in especially in MRI section. So I will read his biography. Munen Singh is a postdoctoral research fellow in MR Research Division at John Hopkinson University. He earned his PhD degree in 2019 IIT BHU Varanasi, where he worked image processing for medical imaging, especially in MRI, with the collaboration of Medical Institute located in Banaras Hindu University itself. Dr. Singh specializes developing reliable artificial intelligence based solutions for the reconstruction and quantification of MRI data, making significant contribution quantifying the multiple tissues parameters from a single scan of a human brain and reducing of overall scan time. Prior to him current role, Dr. Singh was affiliated to Manipal Institute of Technology, where he engaged in both teaching and research in deep learning and MRI data analysis. He holds his master degree in instrumentation from the NIT Kurukshetra and bachelor degree in electronics and communication from CSGM University Kanpur. And I am proudly to say that I think he is few most researchers that is working in MRI especially, and he is core engineering background and working from medicals. So developing MRI for low cost solution is a fundamental goal for India. But you can think the research level of MRI, you have to go to first physics, then read the medical things, then apply in engineering. So it is very difficult and high cutting edge research. So I hope he get the expertise in AI also. So with the use of deep learning, especially physics informed deep learning is a new concept for deep learning, especially for our electrical engineers, electrical and communication engineers. So I would like to request to all my researcher students, please focus in this presentation and try to interact after the session. I will share, or he will also share his email address and everything. We are lucky enough that now he is in India, so we can interact also in whenever we get the chance in NIT Jamshedpur, or if we get chance physically to meet itself this NIT campus. So we can collaborate more things also. In this, I hand over to Dr. Munen. Please go ahead for this lecture.
First, I would like to thank you for inviting me for this great conference and a very wonderful introduction. So now I think I can start sharing the screen.
Yes, sir, please.
Yeah. I think you can see my screen, right? Yeah, from deep learning for saturation transfer MRI, that is STMRI. And here is the outline of the talk. Very first, I will discuss the deep learning and how the conventional deep learning, that is data-driven approach, is different from the physics-informed deep learning method. Then I will introduce saturation transfer MRI, that is STMRI. Then I will take applications of saturation transfer MRI, where we will see how I have used physics-informed networks for the applications of motion correction, tissue parameter quantification, imaging acceleration, and sequence optimization. Finally, we will conclude the whole talk. So we have seen that the deep learning has applications in everywhere. In last 20 years, we have seen specifically in the medical imaging and MRI as well. So this is a good example where we can segment the different region of brain tumor. We can see this is the necrosis at the center, and then there is the enhancing tumor and edema region we can see. So and with the help of for that, what we need a different weighted images. So here we have different sequence of images, and this is another example where we can see that. This is the image of the heart, where it keep beating all the time, and that's why we are living. And But the problem is if we wanted to measure something in that heart image, a cardiac image, just like arteries or maybe the circumference, so it's very difficult because it is not in plane. It's always in deform. So what we need the deformable registration. This is the example of motion artifact correction. This is the image suffered from the motion artifact, and after the motion correction, we can see the very high quality image. And this is the last one is the example of tissue parameter mapping. So this is a recent trend where we can let me take a pointer. Okay, yeah. So this is a new trend. So this is with the help of tissue parameter, we actually get the inherent tissue parameter, and that is not dependent upon the scan parameter values. So here we start using the deep learning techniques. So now we can, as we already know that the data-driven approach try to map input data to output data, and the mechanism to mapping input data to output data actually is very complex. And that's why we think that this is a kind of black box, because we have so many weights, so many bias values. So that's why we think this is a black box. How it's converting, we don't know. But this kind of approach is very, very useful for wide range of application where we have a large amount of training data set. However, we have developed so many physics theorems, we have there are so many physics laws, and the very first thing comes into our mind that why we shouldn't use them, right? So what we can do, rather, along with using the data, we can also use the traditional physics modeling, and this is why we call the physics-informed deep learning networks. So why we need that? Because it makes our networks more interpretable, more transparent, and that's why we can have more faith on the networks, how it is predicting the output. So there is basically, broadly speaking, there is 3 methods to apply physics models into the deep learning approaches. So very first model is very straightforward. So what we can do, we can use the simulated training data set, and then we can train our network on that. So in case of MRI, we have block equations. So block equation is a set of equations, and in that equation, if you have some input data, you can get some output data, and that data we will treat as a ground truth data. That means we can already generate this training data and make a dictionary, and then we can train network on this kind of synthetic data already, what we have, and then we can do the predictions on the real data. So this is kind of end-to-end a neural network where we have inputs and we wanted to estimate some output, and because we already have ground truth data, so we can train this network. But the problem of this kind of approach is the network, since network doesn't give you 100% accuracy, that's why it may not follow the conservation law. And moreover, the network relatively requires more training data set. And sometimes, not in all cases, but in few cases, the generation of training data set itself is a very time consuming. Now, this is another kind of method where what we can do, we rather use training data, rather having the simulated data set, what we can do, we can enforce the physics model, or maybe in the MRI case, we can enforce the block equation within the neural network. And here we can directly call the equations or physics model. And then this network has to, in the very initial layer, we can extract the features, and then we can call the physics model, and then we can try to estimate the output data. But this is a very hard constraint. And sometimes what happens, that it is very difficult, challenging to get the good convergence with such kind of approach. And another thing is the whatever equations we are calling in the neural networks, we need these layers should be a differentiable layers, or these equations should be differentiable, because network has to train and network has to differentiate to learn the values and to minimize the loss. The third method is adding physics model within the loss function. So here we have a data consistency loss, as we can see here. So what we have a ground truth data, we have input and we have output, and here we have already known output values, and this is how we can use the data consistency loss. And then after getting this output, we can use some physics model, and then we can try to have another loss function. And with the help of these two loss function, we can add these loss function and try to minimize both loss function together. And this is how we can have information of the data as well as the physics. So this is a third method. So in this, what the main challenge is, we need to have differential physics equation here, because since we have to minimize the loss, we need a differentiation. So we need to have a differential physics equation. So this is just an example in case of MRI I took, but for your problem, you can have different kind of physics model or equation, but the only thing is required, you have some differentiable equations. And nowadays, there are some methods are also available where if you don't have a differential equation, still you can use the deep learning. Now, as we know that in general, the deep learning or AI can be divided into the supervised and self-supervised learning. Similarly, the physics-informed neural network can also be divided into the supervised and self-supervised methods. So in case of supervised method, we can have the ground truth at the data consistency loss, as well as we can have a ground truth at the reconstruction level. Reconstruction level means where we have output, is the output went to the physics model, and then we try to reconstruct the original data. Right. So this kind of approach is very good, but it typically requires a huge amount. But typically they are very good in convergence, but it requires the huge amount of label data, and sometimes to get the huge amount of label data is very challenging, specifically in medical domain. And this side we have a self-supervised learning approach, where we can see that the physics model itself providing the levels. So this is output, and this output is fed into the physics model, and this is physics model giving you some output data, and that output data is comparing with the input data, and this is how it is trying to minimize this loss function. And in this case, you can see we don't really need a ground truth, and how but the physics model itself is creating a ground truth for us, and the output is basically comparing with the input. That's why we are calling it a self-supervised learning approach. The problem with this approach is sometimes it is slow or difficult to converse. Now I would like to introduce saturation transfer MRI, that is STMRI. So this is an MRI image. We can see the very nice structural information in that, and how we get this information. This information comes from the water molecules. But once we excite the when we provide the RF excitation to the water molecules, we can see this kind of information. But this conventional MRI doesn't have any chemical or physiological information, right? At the same time, this is another image where we can see that this is the another image where we can have the protein information. And in this case, the protein information is related to the water. How much protein is there? This is the amide protein. So this is very high in this case, in the tumor region. But in this conventional MRI, we can see this everything is high. The ventricles are high as well. But this is not a tumor. So it is more specific. So chemical information is more important. But the current conventional methods of MRI doesn't have chemical information. The question is how we can get this chemical information. So this chemical information we can achieve with the help of saturation transfer. So saturation transfer can detect several molecules based on their resonance frequency. So in our brain tissue or any tissue in the body, we can have macromolecule, we can have water, solute, and various metabolites, and they all resonate at different frequency offsets. So what we do, we just tune that particular frequency offset and try to saturate that proton attached to it. And once we saturate the proton attached to it, it start exchanging with the free bulk water in the surrounding. As we can see here, this blue one is start exchanging with the free bulk water, and we keep apply this RF saturation pulse for some time, let's say 2 seconds or 3 seconds, and then what we see after TS time, that is saturation time, the whole water signal gets saturated here. Everything is blue here now. Previously it was white. So once this water gets saturated, we see the decrease in the signal intensity. Previously, we were having a high signal intensity, and after T's time, we keep applying the RF saturation pulse. This saturation intensity goes down, and with the help of S naught and S saturation, when we normalize it, then we can get the amide signal. So here you can see the amide signal. So this is the S saturation divided by S naught, and this is how the signal look like. And here we have amide signal as 3.5 ppm, and some other signal, some other proteins or metabolites at different frequency offset we can have here. So this signal is basically a composite signal. This composite signal have a different metabolites, different proteins. So this signal, we call it a C spectrum signal. So you will be wondering about that, how you can get a one-dimension signal from the MRI. So actually, this is not the one-dimension signal we are getting. This is actually we are getting the images. So here we have images at 10 ppm, one image at 9 ppm. We have another image, and this is how we actually acquire a set of images along the frequency offset. And this signal is actually nothing but the one signal along the voxel Y. So this is how the pattern is changing along the particular this voxel we have chosen here. So now we will talk about the classification of saturation transfer MRI. So saturation transfer MRI includes magnetization transfer contrast, that is called MTC. We can see here in the yellow line, and it includes chemical exchange saturation transfer, that is CEST. It includes amide proton transfer, that is APT, which is a variant of CEST imaging. It includes nuclear overhausen enhancement, that is NOE. So the question is why this saturation transfer MRI or APT CEST is very important for us, because we have discussed just now, and again I would like to mention here, it has a lot of clinical applications. It is very useful for early diagnosis of the tumor, stroke, and various neurodegenerative diseases, because the structural change in conventional MRI comes very late stage, but the chemical changes or physiological changes comes very early, and that's why we can detect any disease at the early stage. Now we can talk about the whole framework of where I have used the physics informed deep learning networks for the sequence optimization. So very first we design a protocol, then we perform the sequence optimization, and then we acquire the MRI data. Once we acquire the MRI data, we can reconstruct MRI data, then we can perform the motion correction, tissue quantification, and risk assessment, as well as the treatment planning. So here we can use the physics-informed deep learning networks for sequence optimization, reconstruction, motion correction, and tissue quantification. So now I will take my very first application of the motion correction in STMRI data. This is the pulse sequence diagram of the MRI, where we can see this here we are acquiring data, and this is here in this time we are applying saturation pulses. So when there is motion during the case-based sampling, we are acquiring the data, there can be a motion. Actually, motion can happen during any time throughout the scan or between the scans. So if there is motion during the case-based sampling, we can see image spatial artifact. There is some lines you can see. This is because of the case-based motion during the case-based acquisition. And this is if there is motion between the acquisitions, so we can see whole image is getting shifted, rotated in 3 dimensions. And and the overall motion effect is the combination of motion during the case-based sampling and motion between the acquisitions. And moreover, we can see that the whole signal intensities are changing as time goes on, because here we are acquiring lot of MRI images along the frequency offset, and that's why the contrast and signal intensity is changing. So to correct motion artifact, very intuitive motion free images, that is ground truth images, and then we can simulate motion into the motion, simulate motion in the ground truth images. Then we can train the network. So we can have in this neural network, we will have the motion corrected images as the input, and the output is motion corrected images, because we have a motion free ground truth images. So for that, very first thing what we need to do the motion simulation. So this is the motion simulation, since motion was happening during all the time during the motion during the case-based sampling and motion between the acquisitions. So if there is motion simulation during the case-based sampling, so how we can perform them? How can we simulate the data set for that? So very first we try to move MRI image up and down, left and right, and rotate, and then we take a full transform, that is we convert into the frequency domain, or called the case-based domain, and then we combine all the information into the one image through the by applying a non-overlapping mask and inverse Fourier transform. And this image you can see have motion artifact in image spatial domain because of the motion during the case-based acquisition. If there is motion between the acquisitions, so we simply translate or rotate image into the 3-dimension X, Y, Z, pitch, yaw, and roll direction along the frequency offset. We can see that the contrast is changing along the frequency offset. So now we already performed the motion simulation. We have a ground truth images. We can do the motion correction, right? But there is some problem. The problem is, to train a deep learning networks, we require huge amount of training data set for, let's assume 5,000 images or so. But in case of STMRI, we have from one patient or one volunteer, we can have hardly we can have a 15 number of data points in a 5-minute or 10-minute of a scan. So it's very challenging to get a huge amount of training data set, specifically in this STMRI. So and moreover, motion is very complex because of the motion is in 3 dimension. It's left, right, and along the Z dimension. Moreover, we can see that image spatial artifact on the images on the plane as well. So the motion is very complex. So what we thought of correcting the motion voxel wise and using the property of the Z transform that just now we have seen. So if we extract out the one voxel from here and plot it along the frequency offset, so this is how Z spectrum look like. And if there is motion, that means the particular voxel is moving up, down, or in Z direction or anywhere, then it will not have the same signal intensity as other voxels have. And this is how we can simplify the motion pattern to correct it. And moreover, because in one image we have around 64,000 soft pixels, and the pixel that is that is a useful pixel that is not having zero values, maybe around 50,000. This is how we can increase the whole data set by the 50,000 times. So this is just one way very specific to our problem. But yeah, this is how we can think of some other problem as well. So this is the proposed motion correction, and we have motion corrected input, and we have a ground truth, and here this network has to learn how to correct the motion with the help of data consistency loss. But what we did, we added another loss, that is, we call it the physics loss, to preserve saturation transfer contrast. That is very specific to this problem. But yeah, you can take some idea how can you use the physics informed loss for your problem. So what we did, we added, we try to estimate some other signal from the motion corrected signal and from the ground truth signal, the same network, and then try to minimize the difference between these two signals. So this is now whole physics informed motion correction using deep learning. These are the results for the motion correction in a tumor patient. This is real data. Here we haven't asked patient to move or perform any motion simulation during the scans. This is the real data. So we can see before motion correction very unexpected signal intensities in the normal appearing white matter region. Here you can see in this region. But when we apply the motion correction technique, we can see that the unexpected signal intensity has been removed, and we can see very high image quality and very clear peritumoral edema region it was observed after the motion correction. So this is how it helped to the better diagnosis. Now I would like to talk about the quantitative STMRI. So just like any other MRI, So STMRI also depend upon the scan parameter values. So here we are changing the scan parameter values, that is TS. TS is the actual saturation time of the RF pulse, and B1 is the strength. So if we are changing saturation parameter, that is TS, so contrast or signal intensity has changed. And in this case, we are changing the B1 value, that means saturation strength, the contrast and signal intensity is changing. Moreover, there is certain methods to calculate the APT signal. So there's the APT pound, AREX, APT weighted. There's several methods, and all methods we observe that giving different signal intensities and contrast. That means actually these methods is not giving these methods are not giving the actually inherent concentration of the amide, but there are a lot of signal got mixed over in C property. That's why signal is how much exactly the APT signal is there and how much exchange rate we have. So for that, by Denmark in 2013, published a paper. Their C tried to estimate the T1 and T2 relaxation time in the MRI images. For that, she suggested that if we pseudo-randomly varied the scan parameter values, we can get a very unique fingerprint. And that's why GC called the MRF, magnetic resonance fingerprint. And we took that, we inspired from that approach, we applied this similar approach in our case, and then we proposed STMR fingerprinting, and we call it STMRF. So in that case, what we are doing, we are pseudo-randomly the saturation of pseudo-randomly varying this, we are having very unique fingerprint, as you can see here. So we are acquiring images like that. It's very different in the contrast and signal intensity. And for this voxel, we can see this very unique fingerprint. And once we have this unique fingerprint, we can match this. We try to find out this fingerprint in this dictionary. And dictionary was prepared with the help of block simulations. And actually, what is block simulation? You were wondering that. So block simulation looks like this. So block simulation is made up of the block equations. So these are a set of equations where if you have the scan parameters and the tissue parameters, this penetration is actually nothing but the signal intensity in the MRI. So once you have if you feed the block tissue parameter into the block equation, you can get the signal. So this dictionary you already have, and then you can find the best match in this dictionary, and you can quantify the tissue parameters in the brain. And this is for one voxel, and for all the voxels, if you keep having this kind of signal, then you will have a map. So here you have an exchange rate between the macromolecule and water. Here you have pool size ratio. Here you have T2 of macromolecule, and here you have T1 of the water. These are tissue inherent proper present, but they will not change if you scan. Either you scan in the Agartala or you scan in the Jamshedpur. These property will not change. But for this, there is some conventional methods were already proposed using block fitting approach. So this is computationally very expensive dictionary matching approach. This is for a small dictionary size. It's very fast, but you will have a lot of quantization error. That's why we need a deep learning. And what we have actually in block simulations, if we feed tissue parameter and scan parameter, we can get the signal, MRI signal. But in reality, from MRI, we already have MRI signal, and we need to have a tissue parameter. That's why we need some inverse model, and then inverse model can be mimicked with the help of deep learning approach. Here, this is the very first deep learning model proposed for this purpose to quantify the tissue parameters proposed by some research group in the Harvard University. But the problem of this approach is this is a data-driven approach, although they simulated data from the block equation, that is physics-informed network, but there is no specific mechanism that can help to learn the inverse block relation. So what we thought of adding one block equation, there is a physics model within this system. But then we realized that block equation itself is very slow. To generate 40 million of training data set, it requires 4 days. And let's assume we need to train this network for 50 number of epochs. That means this network will take 200 days to train this network, and this is a very impractical approach. So what we thought of is replacing these block equations with some other neural network that can mimic like a block equation, and we call the deep learning based block simulation. This is a deep learning based block simulation we called as a deep BS network. So conventional block equation was taking a 106 hours to get a 40 million data set. Now we are getting only in 30 minutes. And you can see here, we replace the deep learning based block, we replace the block equations with the deep learning based block simulation. And here we have two loss functions. One is the data consistency loss, this is loss 2, and loss 1 is the physics loss, physics informed loss. So we found that our proposed method outperformed the existing block fitting approach, and our method was almost 600 times faster than the block fitting approach. And then we performed the validation that really what we are estimating is correct or not. For that, we performed some phantom study. This is cross-link BSA phantom we prepared in our lab. These are the in vivo tissue parameters we obtained, and we compared with the existing block fitting based approach, and we can see that this is very consistent result we got. Our results were very comparable with the existing approach, but the advantage is our approach was around 600 times faster than the block fitting approach. The only difference is in the exchange rate, but we already seen that our method is performing very well on the simulated data set. That's why we are expecting these results are more accurate than the block fitting approach. Then we try to find out the other proteins, that's APT and RNA signal, with the help of these tissue parameters. Now we will see the imaging acceleration. So the existing imaging acceleration approach is about is using the compressed sensing and using tissue quantification. This is two-step approach, existing approach. And now we are proposing to use to perform the tissue parameter quantification directly from the undersampled case-based data. For that, this is a proposed approach, and this is a completely self-supervised approach where we don't need the ground truth and we don't need the fully sampled data. So what we have undersampled data here. You can see that a lot of lines are missing, and then we perform the inverse Fourier transform, we can get the image, and this image has an undersampling artifact. You can see this is straight lines are here, and then we can use some network to convert this data, low dimension data, to high dimension data. And this is the tissue parameter we have here. Initially, we will have a lot of artifacts in these tissue parameters, but as we will train this network, we will have very high quality tissue parameter math. Once we get the tissue parameter math, we are using this physics some physics information block simulation, and another physics information is FFT we will use to get the whole case-based data or whole frequency domain data from the images. And this is how we start filling up the space. So you can see the input was some undersampled, a lot of lines are missing, and once we did the full transform, we have all data here. So this is initially this missing line, but start having some meaningful values, and ultimately we got very high quality tissue parameter maps here. Finally, we replaced the block simulation with the deep learning based block simulation because we wanted to have very fast training. So if we use the fixed undersampling mask throughout the dynamic scan, so we observed some artifacts in the tissue parameter maps. But when we apply the variable undersampling, that means we are uniquely acquiring some data along the dynamic scan. We haven't observed any artifact, undersampling artifacts. This is when we perform 2-point-fold undersampling. Then we have seen a lot of artifacts in the image domain, but when we reconstruct data, the output was very high quality, and output was similar to that. These maps are very similar. This is how we reduce the scan time. Finally, I would like to discuss the MRF sequence optimization, because more acquisitions improve the quantification accuracy and less acquisition improve the scan efficiency. We can reduce the scan time. So in this case, we were using the 40 dynamic scan, But while providing the importance of particular scan, the particular scan is how much important, or in general for you can think of how much importance of particular input, how much importance particular input is. If your input has 40 values, in that 40 values, those 40 values, you can provide the ranking, importance ranking of the all 40 values contributing in the output. So while applying the while providing the importance ranking, and then we put some threshold and selected the most important 10 number of scans or 10 most important features that is contributing to the output. We have here the new scans, and this is how we reduce 4 times. This is a neural network for that. So this is deep neural network. Is very good for feature extraction, and we can get the tissue parameter here. But this network is a kind of black box where we don't know how it is performing. So it's very good it is very good for feature extraction, but very bad for interpretation. That's why we need another neural network, which is a single layer network. And at the input layer, we have a linear activation function, and it is very good for interpretability. That means if weight is very high, that means this particular input is very important. And the output of this network is actually to estimate this feature extract these features, encoded tissue parameters. So this network is so powerful, it can estimate the tissue parameter basically in combination, and then we can apply the feature ranking. We can select some important features from that. So this is how we selected the important how many scans are important for us. So we can see that the 20 number of scans has almost same as good as accuracy as the reference just 40 dynamic scan, and this is how we obtained a twofold acceleration. So this is the initial scan we had reference with the 40 scans, and we ended up to the 20 number of scans. And this tissue parameter, we can see that the reference one and the 20 having a 40 dynamic scan taking almost 4 minutes, and with the optimized one taking only 2 minutes, and we can see very similar performance. When we randomly chosen the 20 dynamic scan, the performance really got very bad. So this is all from my side. Now I have some conclusions. So in this talk, we have discuss that how we can incorporate block equations in the deep learning frameworks to improve reconstruction accuracy. We applied physics-informed networks, physics-informed deep learning networks for the motion correction along the Z-spectral domain, that is one-dimension domain rather than the two-dimension. And we performed the tissue parameter quantification. We have seen that how imaging acceleration can be performed with the help of self-supervised learning approach, where we were not having any ground truth data. And finally, we perform the sequence optimization using IRNet, where we have seen that how can you give the importance ranking to your input to the deep learning approach. And here is my acknowledgements from Johns Hopkins University. Thank you for your attention. I would be very happy to answer if you have any question. Thank you so much. Yeah. Actually, yeah. Yeah, now it's audible. So that's yeah. It depends upon the application. There is no certain answer. I cannot say you for your problem how many neurons you require. Or different application may require a different number of neurons. So so typically, it depends upon it's process of just designing a problem and getting some answer. There is no certain answer for that. Actually, people use 256 or they don't get a good result and they try to increase it. And it depends also on how many layers you are taking, which kind of function you have. So there are so many variables are there. But for that, there's some algorithm has been proposed to optimize the number of neurons, number of layers. So there are some methods are there. Yeah.
Next.
So the next question.
Which one is more accurate and fast? Deep learning of physics or physics informed deep learning?
Only deep learning.
Only deep learning or physics informed deep learning?
So actually, again, I will say that means accuracy means since you have two laws concern in the deep physics informed deep learning. If you cannot means if you cannot adjust those laws, maybe you may have a divergence in laws, and this will end up with you having a very low accuracy. But we are expecting the physics informed laws sometimes to give you the good accuracy, even though accuracy is not that important. Important is here better interpretability. If you are getting something, so you have raising your hand there. That is more important right now. So all the networks more or less have sufficient accuracy. So this is my belief, but yeah, but this is one experimentation.
Anyone else?
Thank you,
Sir,
sir.
okay, sir. I have one query. Actually, I have two query. Sir, so one is, if sir testing accuracy is more than training, sir, what does it mean? In my project, I have seen several times while doing some machine learning and deep learning project in MATLAB, sir, that testing frequency, testing accuracy is coming more than training accuracy. So what does it mean?
Okay, that means that means that what you have your network is very simple. I think so. What you can do that you can add. Okay, your testing accuracy is high. Then you should the output particular time estimate is very similar to that, and maybe your network find very easy to understand it and interpret it. And so what you do, yeah, it's fine. I think it's this kind of case we call it as a I forgot that name. This kind of situation, yeah, you can have this. There's no problem in that, but yeah, I think you should try to taste on a large data set, and that's why you can evaluate network very well.
Sir, actually, such question came from one reviewer that why my testing accuracy is more than training.
Reference is what?
Yeah, actually, I already answered that. Actually, maybe your network is tested on trained on very huge data set that is very complex, and when you are testing that is not that complex. So that's how you are getting very good accuracy.
Okay, sir.
So you
Lastly,
can try to base on that the huge data set.
sir, if I want to use physics informed deep learning network in classification of multi-class, sir, time series data, sir, what will be the steps?
So yeah, I think we can discuss this more in detail. The step is it's difficult to tell because if I know the your actual problem, then we can discuss more detail. Maybe you can compare it with HTML or through the purpose lens.
Okay, sir. Thank you, sir.
Yeah, no.
Thank you so much.
Thank you, sir. Thank you for this insightful lecture.
Yeah.
Thank you, sir.
Yeah.
Okay.
Thank you so much for inviting me for this.
Pleasure, sir. Pleasure. सर अभी ब्रेक होगा क्या 15 मिनट का?
बैच वाला नहीं पूछ पाए। बैच सिमुलेशन दूसरे के लिए एप्लीकेबल है क्या? बैच लॉन्च था।
Now we'll be having a break for 15 minutes and after that we will continue.
फिजिक्स इन्फॉर्म में उसने ब्लॉच इक्वेशन यूज किया है, ब्लॉच इक्वेशन स्पेशली एमआरआई के लिए है या ब्लॉच इक्वेशन हाँ अच्छे हाँ महेंद्र सिंह जो मैं अकेला कार्ड बुलवाऊंगा
Hello, am I audible? Are you all ready?
and is currently a professor at Department of EEE, Buet, Bangladesh. She was the winner of Canadian Common Scholarship for pursuing her PhD study in Canada and recipient of Bangladesh Academy of Science Gold Medal. She is also a member of the World Academy of Science. She has received IEEE TAB Award, IEEE Fourier Award for Signal Processing Committee, IEEE Computer Society Awards, etc. She is the recipient of 2021 IEEE MGA Achievement Award, 2021 Inspiring Women in Academia Award from Bangladesh Brand Forum. She has more than 24 years of experience in leading technical, professional, industrial, educational, women empowerment and humanitarian technology, power and energy related projects at national international level. So I am welcoming Professor Dr. Celia Shahnaz. Her topic of discussion for today is deep learning for biomedical applications. Thank you, madam. Now the session is handed over to you.
Thank you very much for a humble introduction. Hope I am audible to all of you. Just confirmed that I am audible to all of you. Just allow me 1 or 2 minutes, okay? So I just want to thank the organizer for inviting me, and I want to congratulate them for SILCON 2024. It's a great effort. So without further delay, let me share my presentation. Enter screen. Yeah. Share. Please confirm that you can see my screen. Yes, ma'am, we can. Yeah. So I'm just checking. So is it checking? Is it changing to my second slide? Yes, ma'am. Okay. Then we are fine. We can go for it. Thank you very much. We'll be talking about today deep learning for biomedical application. Although I was not with you in person, but I'm very much in spirit with all of you, with your great effort. This is just a brief biography. For your kind information, I request you to visit my website www.celiashahnaz.com to know about me. Also, I would like to request you to visit my Google Scholar profile so that you can know about my papers and you can reach out to me for possible collaboration. Let us discuss with one of our papers that my students have published in a prestigious IEEE Journal of Translational Engineering, Health and Medicine. That student is now doing PhD in Purdue University, USA. And let us know that what is an arterial blood, actually higher oxygen level, as you can see in the left side with the bright red, and venous blood is lower oxygen level, as you can see by dark red. The meaning of hypoxemia is abnormally low blood oxygen. So this is a common phenomenon in ICU, and it is very complicated. So it is associated with the cardiac arrest. That's why it's very complicated. Low oxygen saturation is also a very critical problem with the mortality crisis in the hospital patients. So it is really important to provide an early warning so that we can take necessary intervention. So traditional identification approaches like pulse oximeter is really unreliable because it gives false alarm, missed or delayed identification. So in the literature, there are some machine learning approaches with but they do not use the PPG signal, polyphotosomnography signal. So we propose a neural network based approach to quickly identify hypoxemia from PPG signal. That is the contribution, because PPG signal gives you the condition of the heart. So other methods do not take the condition of the heart so that it can measure the cardiac arrest. So this is the data set publicly available. This is a huge data set, so you can download it and you can see the data balancing for training and testing. Actually, hypoxemia severity classified in three class: normal, moderate, and critical. And this is the overall methodology. And that means we pre-process the PPG signal. And am I audible? Hello?
Yes, ma'am, you are audible.
Okay, so we pre-process this PPG signal and then we send it to the CNN, convolutional neural network block, and after that there is two parallel branches: series convolutional neural network block and residual squeeze excitation block, and then it goes to dense layer before getting the prediction. My now question is that how it is pre-processed by labeling the PPG signal according to the oxygen saturation level. If the saturation is greater than 91%, we call it normal. If it is moderate, it is 85% to 91% saturation level. In case of less than 85% saturation level, we call it very critical. So I really faced it from last 16th October. My mom's saturation level was below 80, and there was a breathing problem and a lot of complications. So this is the practical thing I have faced in my life recently also. Due to lower number of moderate and critical samples, the classes were sampled according to the generative balance data set. So the pre-processed data set is fed to CNN block for feature extraction. So this is important to see our basic CNN block and then the series CNN block, how it works. And then this is the residual squeeze excitation block. If you look at the matrix 125 cross 64, all columns are similar color. And then if it passes through the residual squeeze excitation block, you can see a matrix that is each column with different colors. That means this residual squeeze excitation block is able to differentiate between different classes that has been manifested by the different colors. Okay, so we have explained this, that the squeeze excitations, the global information is performed by applying a global average pooling, and then in the excitation section, two densely connected layers with ReLU activation function are constructed to learn the non-linear interactions between the channel as well as mutually inclusive relationships. The ultimate goal is to give the various weight of attention that are put on individual challenge of the input so that we can see the difference to make a difference. So this is our evaluation metrics like accuracy, precision, recall, F1 score, Cohen-Kappa statistical score. And we compared it with non-parametric models so that we can see the justification of using the deep neural network model compared to the non-parametric models such as random forest, naive Bayes, Kane, and others. Okay, and also we need to see that how many series of CNN blocks we can exploit compared to F1 score accuracy and Cohen-Kappa. It is shown that is 5-6 block is enough, 5 is the optimum. But at the moment, we need to really know that why we really had two parallel blocks and then assemble them, because we have evaluated the series convolutional neural network block and the residual squeeze excitation block individually, and we can find when we ensemble them, their fun score, accuracy score, and Cohen-Kappa score are higher. And comparison of different numbers of channels, it's shown that 64 channels are enough for this, because we cannot take unlimited number of channels. And it is also important to know that how many dense layers and how many nodes. So it is shown that 256, 180, 30, 23 is optimum one. Here comes the efficacy of the model we proposed. If we see the first figure, it shows the model accuracy for validation and training, both the cases. And validation and training both follows the same pattern. But if you see the loss with increase of training in each epoch, each trial, we can see the loss is decreasing. That indicates that our model is very much accurate and very much appropriate by this loss and training graph. And how we are performing compared to the conventional other neural networks such as Inception, AlexNet, VGG, Sextet. It shows that our proposed network is outperforming compared to the existing one in terms of F1 score and Cohen-Kappa score. How we are performing compared to the machine learning approach for hypoxemia, we can see in terms of metric, F1, precision, recall, everywhere, and in each classes, we are also outperforming the existing machine learning approach. So these are some future, because if the heart rate is less than 60 beats per minute, we have to really do some more analysis. So let us move another very interesting topic. COVID did not really leave us. So it is important to have detection of COVID-19 from different imaging techniques, During COVID, I collected these images, and we have published a work that has been published in IEEE Transactions on Artificial Intelligence. My student got the PhD admission in Rensselaer Polytechnic Institute in New York. It's a very good school, and the title is CAPSCOVNet, a modified capsule network to diagnose COVID-19 from multimodal medical imaging. Okay, so multimodal means CT, ultrasound, X-ray, like that. So this is the proposed method. Once we take the ultrasound frame, video frames, slice them, then do the pre-processing, then we send it to the CAPSCOVNet network. And below you can see the bigger picture of the CAPSCOVNet, because there are parallel convolutional block where you can see the parallel blocks, and after that you can see the concatenated capsule block, and finally you can see the decoder block, and finally you can see the interclass separability and the reconstruction. This is our first block, parallel convolutional neural network block. It is used to extract features from input images. You can see the different metrics, sizes, and then concatenated capsule network block consists of primary capsule and a higher capsule layer. You can see the structure, and finally decoder net which are composed of some neurons and then reshaped to different image size. Actually, in this block, we can reconstruct the image. At the same time, this method has the capacity to distinguish between normal pneumonia and COVID, because for pneumonia and COVID, both the cases oxygen saturation level decreases. But how to detect? You cannot observe the image hours after hours. So there should be some automatic detection. If you want to know that how we did it, we did 3 publicly available data set, and we have shown that with pre-training and with enclashi pre-processing, we are outperforming and we are doing our best. And then what is the justification? Capsule network with sequential convolution block or capsule network with parallelly concatenated convolutional block? So we have shown in 3 data set in with all evaluation matrices like accuracy, precision, sensitivity, F1 score, specificity, that it is justified to use capsule network with parallelly concatenated convolutional block because they have the higher value. Yes. Now let's see this table. We compare our proposed method for 2 data set compared to the standard state-of-the-art methods. We can see with the bold values that we are really doing great, and lower table represents that how compared to the other methods we are able to detect a difference between normal pneumonia and COVID-19 like before. We are again outperforming the other methods. This is the GradCam visualization of ultrasound and X-ray samples. The first 4 rows are for a data set, second 4 rows are for different data set. First 4 columns are for normal, second 4 columns are COVID, and the third 4 columns are for pneumonia. Okay, if you look at the 4th row and the 8th row, you can see that how it looks for the normal samples, COVID samples, pneumonia samples, and it's really difficult, but really different, completely different. But you are not able to, it is not possible to able to look at the samples all the time. That's why we need such automatic tool or automatic technique that can really differentiate between these 3 classes. Another work is my students published a capsule network for abnormality detection in musculoskeletal radiography. It has been published in IEEE Access, but question is why this musculoskeletal radiograph? Because 1.7 billion people are suffering with this abnormality, and there are a lot of data processing. This is the basic architecture, and we pre-processing because if you look at 64 cross 64 and 128 cross 120 and 224 cross 224, from visual observation you can see that when there are downsampled the features are pixel size, we can degrade the image quality, but if we increase the pixel size, that more features are included, as you can see by column C. But we do not depend on the subjective observation. We really wanted to know objectively. That's why we had training accuracy and validation accuracy for different image sizes. We also had BRIC score and NIC score. You can see for 2 to 4 plus 2 to 4, we have both increased training and validation accuracy. And also for 2 to 4 cross 2 to 4, we have decreased break score and nick score. That's why it became rational that we go with 2 to 4 cross 2 to 4 so that we lose less feature after resizing. This is the proposed structure of the CAPSNet. Convolutional one has convolutional kernels with activation function. Convolutional capsule layers has 32 channels of convolutional 3D 8D capsule, and class capsule has 2 capsule. Each capsule has a dimension of 2. If you look at this diagram, then you can have a better idea about how it works, and you can see, and there is a routing by agreement algorithm before detecting as normal and abnormal. These are some function used. You can find it in the paper, but question is what type of data you have used it. We have used a Mura data set of 14,656 images, and there is no data imbalance. And this routing by agreement algorithm has been an iterative process, and it is shown for all types of images. Everywhere we can find increase the number of routing. If we do this, training and validation accuracy increases. But in case of some images, if you look at the last but the one, then you can see there is a overfitting happens. To avoid overfitting, we decided to take 4 routing. Let's see how we are doing in terms of Cohen-Kappa statistical score. For all types of images, finger, humerus, elbow, forearm, hand, shoulder, wrist, you can see CAPSNet provided by the green is outperforming the instead provided by the blue. That means we also found the CAPSNet architectures provide 10% better Kappa score with the 169 layers of DenseNet while using 50% less training data. This is a very good, very important thing. And we compare our method with the state-of-the-art techniques and with some training and testing accuracy, and compared to the state-of-the-art techniques, our proposed CAPSNet is providing better training and testing accuracy. And now the loss accuracy graph, compared to our accuracy, their accuracy is low, and compared to our loss, their loss is higher. That's important because it indicates that how we are performing and how accurate our model is. Okay, and another work very interesting, we have exploited cascaded ensemble of features for the detection of tuberculosis using chest radiograph. This is the overall proposed method. You are taking the chest radiograph, and one row you are doing ensemble of the different deep neural network. In another row you are doing the ensemble of the hand engineered features. That finally you are ensembling both the outcomes to get better approach. That means finally you are looking forward to hand engineered and deep learning ensemble values. These are some handcrafted features that we have found, and then we have evaluated the quality of those handcrafted features by Bhattacharya distance and geometric separability index. We can see that everybody has a better values, but we have evaluated them with 2 standard dataset publicly available, and we can see the evaluation matrices accuracy area under the curve, sensitivity to specificity are better when we do the ensembling of all handcrafted features. Now, before going to the deep learning network, we really investigated which I should say, which block or which step is important, and for inception with the DenseNet 169 and ResNet 50, and we can see that the layers with bold colors are providing better accuracy and parametric values. And then what we did, we also investigated that with augmentation and with pre-training, we are doing better if we take the deep neural network ensemble. So once we do this ensemble with pre-training and augmentation, we send them to classifiers like logistic regression, SVM, NN, KNN, and random decision forest. And we can see the logistic regression is providing the better values. Let us compare the whole proposed one with standard state-of-the-art method. You can see with the bold values that we are outperforming them. This is really important to have the good news. Now you see the GradCam evaluation. The first block is for one data set, another is for senior data set. The first row is normal and second row is tuberculosis. And you can see that it's easily distinguishable. And the second column is DenseNet, Inception V3 is the third column, fourth column is the ResNet 150. That means visually it is distinguishable, but we do not want to depend on it. That's why with such type of automatic method we have proposed. Let us see the final one. That was a very interesting topic. Previous work of tuberculosis also published in IEEE Access. So let us see how we have handled distortion classification in laparoscopic videos using DesNet network. This is overall structure. You take the input image, you detect the distortion, you extract the feature and send the feature to the DesNet network. These are the different types of distortion. White Gaussian noise. Actually, noise variance is a key indicator to characterize this image polluted by white Gaussian noise. And another is smoky level detection. Smoky frames tend to have less median values that can detect whether the frame is smoky or not. And uneven illumination level is a ratio of luminance mean to range. It's a great indicator for this change. And blur level estimation, usually they show low variance and less edges. Now, once such a detection is over, we take this input to the DesNet network. The DesNet network is novelties that we have introduced a sequential self-attention layer before the LSTM and before the dense layer. That is the reason it gives a special attention, special emphasis to different detection. This is the model performance. That means our model accuracy for training and validation is higher, whereas loss is lower as expected. Here is the performance accuracy loss Cohen-Kappa score in training and validation. We have better accuracy, lower loss, and very good Cohen-Kappa score. And we evaluated the performance of our method on unseen data too, so that we can get more challenge. And we can see the accuracy Cohen-Kappa score did not decrease much. So finally, the performance compared to the all methods, we were third in rank for our accuracy, first in timing, because it is very important to detect is very fast, because we have to take a mitigation plan, because there will be operation involved in microscopic laparoscopic videos. So distortion classification should be very fast. As I'm an advocate of women, I know many women and children have skin diseases, and we feel shy to talk about it. So we are employing all our deep learning network for automatic skin cancer detection and classification, so that we can support the men and women and children. And these are some of my individual awards. And this is some of my group awards, especially these are society awards under our leadership. IEEE MBS Bangladesh chapter, Engineering, Medicine, Biology Research Bangladesh chapter has received 2020 EMBS Regional Outstanding Chapter Award, and under my leadership, Signal Processing chapter got the certification. And as a Global Women in Engineering chair, this is the website of the Global Women in Engineering. Please visit our website so that you can know the membership values, initial funding, special funding, travel grant, IEEE Family Cares Grant Program, IEEE WA Day, IEEE WA Climate Tech, Pitch Idea, Pitch Competition, competition, IEEE WI workshop, reskill and upskill workshop, IEEE WI innovation and entrepreneurship workshop. Those are the different program values has been launched under my leadership along with my amazing team. Hope you will get the benefit and you will utilize it for promoting diversity and inclusion. So with that said, I really want to thank you once again and thank you for your patient hearing. If you have any question, I'll be ready to respond. However, reach out to me for any time, and I'm available in website, email, LinkedIn, Facebook, Twitter, and any social media. So it will be great honor to support each other. Thank you very much. Hope to meet you soon in future. Thank you. Hello. Hello, Mitra. Yes. 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 Yeah. No, no. This is an honor. This is an honor.
I hope in next future also we'll be definitely going to get the similar kinds of helps and support from your side.
Yes, I will visit you, and most important, I will invite you to the conferences in Bangladesh at the closest.
Yes. Actually, madam, I also had the similar planning to invite you physically to come here. So because of the first time I am hosting this, I could not manage up all those things. Lastly, I had information that we had to give some information to the Ministry of External Affairs. So I avoided that part. So it was not in my hand. So I just avoided that part.
No problem. Everybody is going through some challenges, and hopefully we will all overcome those.
Definitely, we are going to get out of the problem very soon. So thank you, madam, very much for your kind words, and you have given enlightening lectures. Definitely, the audience has learned so many things from your lecture. We will definitely be interested to collaborate with you, madam, or with your university in near future. That's sure.
It should not be a populist lecture. It should be a long-term planning.
Yeah.
And if we can collaborate with each other, any conferences that will be great.
Kojan join kose Bangladesh থেকে student.
বাংলাদেশ থেকে দেখছি
Madam, this for your information, in our NIT also this time few students, I do not know the exact count, mostly 3 or 4 has joined NIT Agartala for BTech program this year only. Earlier also we are having some MTech scholars from Bangladesh in our NIT. So actually this time we had a plan to have more than 10 to 15 students to be joining here. So because of that some mishappenings, it has limited to 2 or 3 students. Might be because of some fairness among them. So thank you very much, madam. I think we'll overcome this and soon we'll meet. Thank you. Thank you, madam. Namaskar. Bye-bye. Thank you, madam. You can leave. Bye.
So এখন তো লাঞ্চ ব্রেক না লাঞ্চ ব্রেক
Hey, stream close. Second session after that. Hey, everybody come, please come forward. Photo. There will be one photo. Please.
मैंने एक भी फोटो नहीं खींचा
No, come forward and see.